Hi everyone, today we'll start with the module 2, that is numerical problems on 1D bar element. So in this we'll see the problems related to straight bar and the tapered bar as well as stepped bar. So for this before starting these problems we should know what are the steps which are involved in this. The first step in solving a numerical problem on 1D bar element is the given problem is to be discretized in the form of number of elements, and each element has to specify with number of nodes. This is we will see in the further when we will solve the problem. Next, in the step 2 we need to define the stiffness matrix for each element. So stiffness matrix for 1D bar element is given by A into E divided by L in the matrix 1 minus 1 minus 1 1, where A is the cross sectional area, E where A is the cross sectional area and E is Young's modulus, L is length of the element, and this is how we need to specify the stiffness matrix of element. Once we specify the stiffness matrix, then we need to do the global stiffness matrix, that is nothing but we need to add all the stiffness matrix of elements and we need to form a global stiffness matrix. Once we form the global stiffness matrix, then we need to go for the global displacement vector, that is nothing but q is equal to q1 q2 q3. This is how we need to define the global displacement vector. Similarly, we need to define the global load vector, that is nothing but f1 f2 f3 fn. So these are nothing but forces which are acting at the particular nodes. After once we define all these things, we need to write the equilibrium equation, that is nothing but k into q, which is equal to f. This is the equilibrium equation. From that we need to calculate, from that we need to apply the boundary condition, that is nothing but elimination approach and penalty approach. In the further problems we will understand what are the elimination approach, what is penalty approach, once we will solve the problem. See, after at the end of the step, like the step number 5 is to determine the stresses, which is nothing but stress is equal to Young's modulus into strain, and the strain for the 1D bar element is given by 1 divided by L minus 1 1, and here into we have u1 u2, that is nothing but displacement at the point at node 1 and displacement at point node 2. So if you want to find the strain in the first element, you need to write u1 into u2. If you want to find displacement at the second strain in the second element, you need to write u2 and u3. Like this we need to solve. So this is how the steps. Now we will see one problem, you will understand how to solve the things. Now here we have the question paper June-July 2014. Question number 4. Consider the bar as shown in the figure. Using elimination method of handling boundary condition, we need to determine nodal displacements, stress in each element, reaction forces. These things we need to define. In the problem it has been given the length of the element is 75 here, and here 75, which is nothing but the point at where the load is applied, and here the second length is 60 mm. Now if you see this figure, in this the both ends are fixed, and it has been given the area of this stepped bar is 150 mm square and the area of this is 250. Right, now once we see this problem, next we need to do, like we'll see how to solve this. Like the steps are given like this here. First step, like the thing is, when we see the problem, we need to analyze the things where we need to model and discretize. The first step of FEM is to modeling and discretizing. In that what we do, wherever the step of the bar is given, there we need to do an element, like from here to here one element and from here to here second element, these two elements, and the first element is given like this, the second element is given is like this, and the first element is connected between node 1 and 2, and second element is connected between this 2 and 3. This is how the stepped bar is formed. But in this problem we have one more point here, like at a 75 mm, at a 75 mm from the fixed end, the load is applied, that is nothing but 10 kilonewton here. So due to the application of this load in between this first element, we need to form one more element in between this. That is what we can see here. That is what we can see here. So that's what I have formed here. Like this is the first element from 1 to 2, that is nothing but from here to here, this is the first element, and from here to here this is the second element, that is nothing but this one, and from here to here this is nothing but our third element. Why we have formed this second element? The second element we have formed because we have a load which is acting at a length of 75 from the fixed end. For that purpose we have formed one more node to define that load. Clear? Whereas this load 20 kilonewton which is acting at this point means the load is acting at this direction, means the load is at this point. So there is no need of defining the one more node here, because here it has been given the application of load is at this point and the application of load is at this point. So here we have defined one more node. When you define one more node, we formed here two elements. Totally how many elements? Three elements. First element, second element and the third element. These are the three elements which we have formed, right? Okay, fine. So this is how the first step follows. Next, the second step in this is like here the given data A1, area of this total element is 150 mm square, area of this is 240 mm square is given. Next, Young's modulus, it is given 200 gigapascal, which we have written 200 into 10 raised to 3 Newton per mm square. Once we write all these things, once we do discretizing and modeling, next we need to define the stiffness matrix for each element. That is nothing but for a bar element we can write stiffness matrix K1 is equal to A1, A1, E1 and L1, right? Where A1 is nothing but area of the first element, that is nothing but this one, area of the first element, that is nothing, first element, area of the first element, that is nothing but 150 mm square, which I have written here 150 mm square. Next we have the Young's modulus E is equal to 200 into 10 raised to 3 and the length is 75 mm. Once we simplify all these things, we will get this data. K1 is equal to 10 raised to 5, 4 minus 4 minus 4, 4. Here we have written 1 and 2. Here we have written 1 and 2. That is nothing but it shows this first element is connected between node 1 and 2. This is how this represents. Similarly, next we need to find the K2. K2 is nothing but elemental stiffness matrix for the second element. This is our second element. Second element is nothing but second element which is connected between node 2 and 3. So here we need to substitute A2. A2 is nothing but area of the second element. Again, if you see the figure, area of this entire stepped bar is 150 and area of this bar is 240, but the our element is here. This is our second element. So area is 150. So that's what we have substituted here. 150 into Young's modulus is 200 into 10 raised to 3 and length is 75, which you can see here. The length is 75. Once we substitute this, and here we have given 2 and 3, that is nothing but the second element. This is element second, which is connected between 2 and 3, which you can see here. The element second, which is connected between 2 and 3. This is our second element. So once you write all these things, once you simplify, the same answer you will get. That is nothing but 10 raised to 5. 4 minus 4 minus 4, 4, which is connected between 2 and 3, not 2 and 3. Similarly, we need to find stiffness matrix for the third element, that is nothing but this third element. Third element is connected between 3 and 4, right? Here again we need to write A3EL3. A3 is nothing but cross sectional area of the third element, which is given here 240 mm square. That's what we have written here. 240 here. Similarly, next we have Young's modulus, that is nothing but 200. Next we have length 60, 60 we have written here 60. 240 is cross sectional area, 200 into 10 raised to 3 is nothing but your Young's modulus, 60 is your length. Then this 3 and 4 nothing but the nodes where it is connected. So once you simplify this, you will get this answer 10 raised to 5. You take it outside, then you will get 8 minus 8 minus 8, 8, which is connected between 3 and 4. Once you form this, the next step is to form the global stiffness matrix. What is this global stiffness matrix? How we need to form this? Let us see. So here, since we have 3 elements, right? We have 3 elements, element 1, element 2 and element 3. 3 elements. So each element is connected between 2 nodes. First element is connected between 1 and 2, second is connected between 2 and 3, third is connected between 3 and 4. 3 elements, 4 nodes. Our global stiffness matrix should be like 4 by 4 matrix. We have 4 nodes, so it should be 4 by 4 matrix. That's what we have written. 1 2 3 4, 1 2 3 4. This is how we need to write 4 by 4 matrix. Once you have written this 4 here, 4, next we need to know how to put these values. We will see now. So see here, this is the first row, this is our first column. So this element we need to see. First row, first column is 4. How it has came? See, we need to go for the K1 matrix here. In this K1 matrix, you can see here, this is your first row and this is our first column. So first row, first column, you can see this is our 4. Clear? In K2 matrix, you can see here we don't have any first row, we have second row here. We don't have first row, so we need to eliminate. Similarly, we can see here in the third stiffness matrix we don't have first row, so we need to better go for this one, K1, where we have first row, first column, that is 4. That's what we have written in this format, that is 4 here. Clear? Once we substitute that, next we need to go for first row, that is nothing but here, first row, second column, that is nothing but minus 4. How it has came? Let's again go for here. Here you can see the elemental stiffness matrix K1, where we have first row and second column. Here you can see this minus 4. That is nothing but first row, second column, we have minus 4. But you can't find that first row, second column here, because we have second row here and third row. In this here we have third row and fourth row. We don't have any first row here, so you need to eliminate all these things. We need to write only these things. First row, second column, that is minus 4. That is what we have written here. First row, second column, that is nothing but minus 4. Once we have substituted this, next we need to find first row, third column. What is that? First row, third column, this is nothing but 0. how it has came, see here. Again if you go here in this, we have first row here, but we don't have any third column. We have 1 and 2 column, we don't have third column. If you go here, we don't have any first row, we have only first row here, we don't have first row here. So it is better, like nowhere we have like first row, only we have here first row, and we don't have third column we don't have, so we have written 0 here. Similarly, if you see here, we have again the first row, we don't have fourth column, we have one and first and second column only. Again in this we have second and third column, we don't have first row, so we have written here 0. Yeah, 0. Once you have written the elements 4 minus 4 0 0, the same thing you need to copy here, because a stiffness matrix is nothing but it is a symmetric matrix. So minus 4, this is 0 and this is 0. Once we have written these things, next we need to go for second row. Next is nothing but our, this is second row, second column, that is nothing but 4 plus 4. How it has came, we will see now. The second row, second column, if you go here in the first K1 matrix, you can see here we have second row and this is our second column, this is nothing but 4. Next in the K2 matrix, if you see here, this is the second row and this is the second column, we have again 4 here. In K3 matrix we don't have any second row here, we have third row and fourth row, we don't have any second row, so we have only the second row, second column in these two. Like here we have second row, second column, that is 4. Here we have second row, second column, that is 4. So 4 plus 4, that is nothing but 8. We have written 4 plus 4 here, that is nothing but our second row, that is nothing but our second row, and where it is, okay, sorry, that is nothing but second row, second column, sorry, this is nothing but second row, second column, 4 plus 4. So once we form second row, second column, next we need to go for second row, third column, that is nothing but second row, third column, it should be minus 4. How it has came, we will see now. If you go to K1 matrix, here we have second row, but we don't have third column, we have second column itself, so here we have 0. Next here, if you go to second K2 matrix, that is stiffness matrix for second element, here you can see the second row and third column, that is nothing but this one, second row, third column, this is second row, this is second row, third column, that's what we have, minus 4. Here in this we don't have second row, we have third and fourth, so here it is 0. Only we have here second row, second column, here we have second row, third column, we have minus 4. That's what we have written here, second row, third column, which is nothing but minus 4. I hope it is clear. Next we need to write second row, fourth column. What is that second row, fourth column? See, if you see here, we have second row but we don't have fourth column, so let it be. Next here, if you have, we have second row but we don't have any fourth column, we have 2 and 3 only, we don't have 4, so it is 0. Here we don't have second row, so it is better here we need to write 0. Understood, right? Next here you can see, once we write this, now you copy the whole thing here, that is nothing but you need to copy this, minus 4, this is 0. Once again you can see here, once you have written this equation, the second row, you need to copy these things, since it is a symmetric matrix, 4 4 0 0. Next we need to go for the third row, third column, that is nothing but this is our third row, this is our third row, and this is our third column, that is nothing but 4 plus 8. How it has came, we will see now. Third row, third column, right? Here in the first matrix we don't have any third row, we have 1 and 2, so you leave that. Next here in this we have third row and third column, that is nothing but this 4 element. This is the third row, third column, we have 4. Again here third row, third column, we have 8. That's why we have written here 4 plus 8. Next you can see the third row, fourth column, that is nothing but minus 8. How it has came, we'll see. Here third row, fourth column, right? In K2 matrix we have third row but we don't have fourth column, so here it is 0. See here we have third row but we don't have fourth column, we have 2 and 3, we don't have fourth column, it is 0. Next if you see here, if you see here in the K3 matrix we have third row, fourth column, that is minus 8. That's what we have written here, minus 8. That is nothing but third row, fourth column. Once we have written this, once we form these things, next we need to write the symmetrics, that is nothing but minus 8 we need to write here. Next fourth row, fourth column we need to find, that is nothing but here the fourth row, fourth column. You can see here fourth row, fourth column, that is nothing but 8. Here in this matrix we don't have fourth row, here in this matrix we don't have fourth row, so it is 8. We have written this. Once we form, you just simplify this, that is nothing but 4 minus 4 0 0, 4 minus 4 0 0, minus 4 minus 4, 4 plus 4 is 8, minus 4 0, minus 4 0. Next we have 0 minus 4, 8 plus 4 is 12, that what we have written here, 12 minus 8 is written here. Next 0, next we have 0 0 minus 8 8, 0 0 minus 8 8. So we have formed the global stiffness matrix. Once we form global stiffness matrix, next we need to go for the global load vector, that is nothing but the load which is acting at each node. Here our problem is given like this, like we have a stepped bar having 3 elements, right? So element 1, element 2, element 3, 3 elements, and each element is connected to 1 2 3 4. Each element is connected in 2 nodes. First element 1 and 2, second element 2 and 3, third element 3 and 4 node. Clear? So the force acting at the first node is given by F1, second node F2, third node F3, fourth node F4. That's what I have written, F1, F2, F3, F4. If you see this problem here, the load application at this point F1 is 0, since we don't see any force here. At this point we have force, that is nothing but F2 is equal to 10 kilonewton, which we can write 10 into 10 raised to 3. Similarly at this node, this is the node 3, at this node we have force, we have the force which is acting 20 kilonewton, and at the fourth node, at this node we don't have any force, so we have written F4 is 0. Those things you can see here. F1, that is nothing but 0, F2 is 10 kilonewton, 10 into 10 raised to 3, F3 is nothing but minus 20 into 10 raised to 3, because the force is acting in negative x direction. You can see that here, negative x direction. minus 20 kilonewton. That's what we have written here, minus 20 into 10 raised to 3. Once we form global load vector, next we need to go for global displacement vector. Global displacement vector is nothing but the displacement which are occurring at each node. Nothing but at node 1 we have u1, at node 2 we have u2, at node 3 we have u3, at node 4 we have u4. These are nothing but 4 displacement at each node. That's what we have here, u1, u2, u3, u4. That's what we need to find. Once we write global load vector, global displacement vector and global stiffness matrix, then we need to go for equilibrium equation. What is that equilibrium equation? We know that stiffness is equal to force per unit displacement, F by U. U is nothing but unit displacement, F is nothing but force. We can write this equation as K into U is equal to F, where K is the global stiffness matrix, U is the global displacement vector, F is global load vector. Now that's what we have substituted here. This is nothing but our global stiffness matrix, this is nothing but our global displacement vector, and these are nothing but global load vector. Okay, so once we written like this, next thing is to apply the boundary condition. That is nothing but step number 4, that is application of boundary condition. Here in the problem it has been given, if you see the problem, it has given using elimination method of handling boundary condition, that here we have used the elimination method. What is that elimination method tells? Like whenever we have a stepped bar like this, we have stepped bar, it is fixed at the both ends, right? So at node 1 it is fixed, at node 4 it is fixed. For that, what we have done, like elimination method of handling boundary condition tells that wherever there is a fixed boundary condition, there we need to eliminate corresponding rows and columns of the equilibrium condition. Like this is the equilibrium equation. In this equilibrium equation, that's what we have written here, in that the first row, like the first and fourth node of the given problem is fixed, so we need to eliminate first row, first column. We need to eliminate first row, first column, fourth row, fourth column. Once we do that, we left out only with these things, 8 minus 4 minus 4 12. Those things we have written here. 10 raised to 5, 8 minus 4 minus 4, these are things which I have written here, and it is left out with these things, that is nothing but u2 u3 10 into 10 raised to 3 minus 20 into 10 raised to 3. These things we have written here. Now we need to simplify these matrix. It is very easy, like you have learned already. You just simplify these things, you will get u3 as minus 0.015. There is no need of simplifying like this. You can use your calci to equation to your unknowns, where you will get the same answer, u3 and u2. So once we will get u2 u3, we know that displacement at node 1 is 0 because it is fixed. u2 you have found out the displacement is 0.0055. u3 it is minus 0.015 and u4 is fixed, so displacement is 0. So this is how we have found the nodal displacement, means the displacement at each node. Once we find out the displacement at each node, next we need to find the stresses in each element which is asked in the problem. So stress can be found out by using this formula, that is nothing but stress in each element. Since we have three elements, we need to find three stresses, means stress in each element. So to find out stress in the first element, we have written E divided by L1 minus 1 U1 U2. This is the formula where E is the Young's modulus, which is nothing but 200 into 10 raised to 3, L1 is 75, and we have minus 1 that is nothing but given the formula. U1 U2 are nothing but U1 is fixed 0, U2 which we have found out, that is nothing but this one, 0.005. Those things if you substitute and if you simplify this matrix, you will get sigma 1, that is nothing but stress in the first element is 13.3 Newton per mm square. Once you do this, next step is nothing but you need to determine stress in the second element. The same thing again here. In the second element, we need to define E divided by L2 minus 1 U2 U3, means second element is connected between node 2 and 3, so we have written 2 and 3. So E is nothing but 200 into 10 raised to 3. Next L2 is 75 minus 1 here, U2 is nothing but 0.005, U3 we have found out, that is nothing but minus 0.015. So if you simplify this, you will get this answer, that is nothing but sigma 2 stress in the second element is nothing but minus 53.33 Newton per mm square. Once we find out the stress in second element, next we need to find the stress in the third element, that is given by again E divided by L3 minus 1 U3 U4, because the third element which is connected between node 3 and 4, since we have written 3 and 4. U3 is given by minus 0.015, U4 is 0, you substitute the data, you will get sigma 3 is 15 Newton per mm square. Once we find stress in the third element, next we need to find the reactions. So reaction forces can be given by R is equal to K into U minus F. This is the formula to determine the reaction forces, where R1, R2, R3, R4, where R1, R2, R3, R4 are nothing but reactions at each nodes, which we need to find. So here how to calculate this is nothing but you need to write K, global stiffness matrix K, and U is nothing but your global load vector, which you have found U1, U2, U3, U4, and this is nothing but F1, F2, F3, F4. Once you find all these things, once we have written this, next you multiply this row and this column, that is nothing but you have written 4 into, like we can see here, this 4 into 10 raised to 5 into 0, that's how I have written here. Next minus 4 into 10 raised to 5 into this, that is nothing but 4 into 10 raised to 5 into 0.05. next we have 0 nothing plus, anything multiplied with 0 is 0, so you need to multiply this is 0, that's what we have written here. Next minus this one. So how to multiply this? First row first column minus this one, that is nothing but 0. Next second row first column minus 10 into 10 raised to 3. Next third row first column minus 20 into 10 raised to 3. Next fourth row first column minus 0. Once you substitute all these things, you will get R1 as minus 2000 newtons, R2 as 0 newtons, R3 as 0 newton, R4 as a 12,000 newtons. Now this is how we need to calculate the reactions at the fixed points, reactions forces which are usually occurs at the fixed location. So hence we have solved the question paper problem of 2014 June July. So please see this video fully, and if you don't understand, comment below, I will answer your all questions. Thank you.